Hi, everybody. Mary here, and it's week 11 in our basic chemistry class. And this week, we're going to depart from a lot of the chemistry we've been talking about, and we're going to spend some time talking about energy, and more specifically, spend some time talking about heat. But this is our story so far. We've been talking about chemical reactions. We've been writing those reactions, and a chemical reaction is like a recipe. We've been employing our old friend, the mole, because that mole allows us to ramp a recipe up, making it larger, making it smaller. We have used different types of reactions, sort of like there's different types of parts of a cookbook, and that allows us to predict outcomes. Well, now we're going to talk about energy. A lot of chemical reactions are exothermic, meaning that heat exits. Some are endothermic, meaning that heat is taken in. But energy is an important idea in all of chemistry. So what exactly is energy? What are the various types of it? And how does energy transform from one kind of energy into another? So energy is a different thing because it is not matter. It does not have mass. You cannot put energy on a balance and weigh it or come up with a mass for it. It is invisible. It is a property of matter. It is not matter itself. So this can be a tricky idea. Let's take a look at these pictures. If I show you this bicycle going at a high speed and this bicycle sitting still, and I ask you which one has more energy, your gut reaction might be this one going high speed, and you'd be correct. If I showed you these two very large boulders, and I showed you one sitting on the edge of a cliff and one sitting on the ground, if you assumed they were the same size, which one possesses more energy? Now, this is a little bit trickier, but you might say the one sitting on the edge of the cliff, but you might not understand why. And that's what we're going to talk about today. All objects that possess energy can move other objects. That's what energy does. Energy is defined as the ability to do work. Now, work in science is defined as the ability to apply a force to move an object through some sort of distance. If an object possesses some energy, it can actually force an object to move. So the bicycle has some speed, and if some unsuspecting little bug flew in front of it, it could apply a force to that bug. If our unsuspecting little bug was down below where this poor little rock fell, it could apply a force to that bug. The electricity going through these power lines, if a little unsuspecting bug was there, poor bug, I'm picking on him, it could apply a force to that bug and it wouldn't make that bug healthy. This bullet flying through this rose could apply a force to that bug. So anything that possesses energy can move an object some distance. That's that definition of energy, the ability to do work, and work means moving something. Now, there are two big, broad categories of energy. One is called kinetic energy, and the other broad category is called potential energy. Now, there are lots of different kinds that fall into both piles, and we'll talk about those in more depth in a minute. But kinetic energy is energy something has due to its motion. So these are not two identical bicycles, but if they were, the bicycle in motion has more energy than the bicycle that is standing still. Something that has velocity has more energy than something without it. Potential energy is defined as the energy something has due to its position. A rock on the edge of a cliff possesses energy just because it potentially could fall and go and splat our poor innocent little victim bug. Where the rock that's already on the ground, well, it's already there. It can't go any further down, so it doesn't possess the potential to fall. Kinetic energy, this energy of motion, how much kinetic energy an object can have depends on two things: its mass and its speed. So let's talk a little bit about speed. If I take a small bullet, like a 22 bullet or a 380 bullet, something like that, it's possible for one person to toss it to another slow enough that it would cause no damage whatsoever. It would be like tossing a softball. But if that same small, low mass projectile is shot with a very high velocity, it did a lot of damage to the rose and it could do damage to other things. So speed is a component to amount of energy that an object can have. Here's another example. When you look at stopping distances for an automobile, the faster you're going, if you're going closer to 70 miles an hour versus going 30 miles an hour, your overall stopping distance is going to be 75 feet at 30 miles an hour. But at 70 miles an hour, your stopping distance is going to be closer to 315 feet. Why is that? Your car brakes, has to take that energy and change it from an energy of motion into an energy of heat. It has to transform one form of energy into another. And there's a lot more energy at 70 than at 30. The amount of kinetic energy something has also depends upon mass. If you throw a low mass object like a tennis ball at your dog, it's easy for you to throw, it's easy for the dog to catch. You try and throw something large like a medicine ball, which is used for conditioning, that ball has a very high mass and that builds up muscles because it takes a lot of energy to throw it and to catch it. One of my favorite stories is the fact that long ago and far away, my husband and I bought a fifth wheel trailer. This is not a picture of us, it's just one I captured off the internet. But in my mind, I know when I'm coming in my little car up to a stop sign, I mentally do the calculations. I know when to apply the brakes, so I come to a nice stop. And when we first got this fifth wheel, my husband said, go forth, learn how to drive it. So he had it hooked up, sent me forth in the country roads, and I started trying to drive with the fifth wheel behind the pickup truck. And I came down to the end of our road with this big truck and very massive trailer behind me. And I did the mental calculations in my head and said, oh, I'm going to stop where I normally stop. But I had so much more mass. There was so much more energy that had to be converted to heat by the brakes that I totally miscalculated in my brain. And I went, phew, and I blew straight through that stop sign. And it was a matter of I mentally was not accounting for this increase of mass and increase of energy. Now, potential energy is different and sometimes a little more tricky to visualize. This is energy due to position. And energy due to position depends upon three things: mass, distance between the objects, and the force drawing those objects together. So let's talk first off about distance, the distance between two objects. If we have a person that's going to jump and land on an inflatable ducky, if he jumps a very short distance, he's not going to be able to do work to the ducky. Okay, energy is defined as the ability to do work, which means exert a force through some sort of distance. If he jumps a very short distance, not going to do a lot of work to the duck. If he jumps a larger distance, he's going to splat the duck more. If he jumps a further distance, splat the duck even more. Jumps from a very high distance, more energy that he possesses, and it's going to be a lot more energy that he can give that duck, and that poor inflatable duck is going to get a beating. Here's an example that many of us have experienced. If you take a simple rubber band and you stretch it a little bit, it doesn't take a lot of energy to stretch it a little, but if you got snapped with it, it doesn't hurt very much. If you take a rubber band, it takes a lot of energy to stretch it a long way. And if you got snapped with that, ouch, that's going to really, really hurt. And that's because the larger the distance, the more potential that it contains energy that it can give something else. Same thing happens with molecules. Two molecules that are relatively close together have a potential energy between them because of their distance. You have to put in work. You have to pull those molecules apart. And If those molecules are then allowed to snap back together, more work can be done. More energy is stored. This is more energy is stored in molecules that are further apart, and less energy is stored in molecules that are cuddled up really, really close. Potential energy also depends upon mass. Let's say that you have a small child up a tree and the small child says, "Catch me, Daddy, catch me, Mommy, catch me, Aunt Frida." Well, if they first throw down their rag doll and the rag doll weighs nothing, it's just a pile of fluff, you catch it, beep, it's easy. But you take a 30, 40-pound kid and they hit your arm, it's a lot to hit you. And it is the same height, it's the same distance, it's the mass. The more mass, the higher that is, the more potential it can do work to you. There is energy stored because the child is at that height. And if he falls, bam, it's going to do work to you. There is stored energy in that height. Same thing happens with a rock. A rock on the edge of the cliff, that's a big rock. When it falls, our poor little pretend bug really going to get hit. If we have a pebble on top of the cliff and bugs down here, if the pebble is small enough, it could be like a grain of sand. It might disturb bug, but it's not going to do him a lot of harm. And then there's the last thing that affects potential energy, and that's the force pulling the two things together. Well, there's lots of different kinds of forces. Spring forces. If you have a little spring that's inside of a pen, well, those springs are kind of weak, and that's not a big force. You take a big force like a garage door spring, that is a big force. So if this snaps back together, there is a lots of energy that can be stored in a big spring. Very little energy that's going to be stored in this little spring. When you start talking about electrical energy, a battery is 1.5 volts if you're talking about a little AA or AAA battery. That voltage is the electrical potential between one end, the positive end, and the negative end of the battery. If you put something like a light bulb between the positive and the negative, when the electrons are allowed to flow, they go through the little coil and they make that light bulb light. Now, 1.5 volts is a small electrical potential. You get high voltage power lines, these can be well over 10,000 volts. That is a way of measuring a big electrical potential energy. Another example of potential forces are gravity. On the Earth, the force of gravity pulls us down with an acceleration of gravity of 9.8 meters per second squared. Well, on the moon, it's 1/6 as much. And so on the moon, the force is going to be much smaller. On the Earth, much, much bigger. This energy stuff can be a little weird, folks, but we're going to spend all week talking about it. All right, see you soon. Bye-bye.